Everybody, I was told I should first introduce myself before introducing the speaker. I'm Aruna Sivakumar. I'm a professor of energy and transport here at the UCL Energy Institute. And before I introduce our speaker tonight, I've got a number of announcements, plural, to make. First of all, the unlikely, but still existing danger of fires. There are apparently two escapes. One is in the back over there, so after you enter straight ahead. But as usual, the closest exit may be behind you, and this is the entrance door which you entered from. The event itself is about 1 hour, and our presenter will talk for about 45 minutes. And she just told me that she actually loves to be interrupted and ask questions during the talk if something is not clear. And afterwards, there's a Q&A session for 15 minutes. So in about 1 hour, you are all invited to join us to the first floor, in which there's some drinks and food waiting. I inspected the food, it's very good, I can assure you. And there's also only one catch. You have to get out of the building before the UCL folks go out, because the doors will be locked at 7 o'clock. So if you wait longer, it's no problem, unless some of us are still around who can help you leaving the building. Having said that, now it's my great pleasure to introduce Aruna Sivakumar. Aruna is a lecturer in travel behavior and demand modeling at the Center for Transport Studies at Imperial College, London. She also leads the transport work streams in multidisciplinary research projects such as the BP-sponsored Urban Energy Systems project, about which I assume we're going to learn tonight a little bit, and the EPSRC-sponsored Digital City Exchange project. Aruna is a young member of the Transportation Research Board, TRB, Committee on Travel Behavior and Values, an elected member of the Executive Board of the International Association for Travel Behavior Research, and a member of the Methodological Innovations Committee of the European Transport Conference. It's so difficult.
I know.
Aruna holds a PhD and Master of Science in Transportation Engineering from the University of Texas at Austin, which is one of the choice modeling hubs in the US. And her research interests include econometric models of demand, travel behavior, and the role of ICTs, integrated urban systems models, and transport policy. This is where I stop, and I give the floor to Aruna.
Thank you. Thank you, Andreas. Well, good evening, everybody, and thanks for showing up. A couple of things before we go ahead. One, I haven't been too well today, so I'm going to speak a little softer than I usually do. I'm usually so loud you can't sleep. It comes from talking to a class of about 100 students and trying to keep them awake. So I'll be a bit softer than usual, but if you have trouble hearing me, do let me know in the back, and I'll try and speak up louder. I'll also be a touch slower than usual because I seem to be running out of breath today for some reason. The second thing, which Andreas was mentioning, is I like to be interrupted when I'm talking, because if you have questions, I'd much rather you raise them when we're on the topic as opposed to when I've moved on, or at the very end when there's no connection with what I'm talking about. So if you have a question, go ahead and raise your hand and we'll discuss it. And I can always squish bits or expand bits as necessary. The third thing is a lot of what I do is econometric demand modeling and integrated systems level modeling. In today's lecture, basically, I'm trying to present an outline of all my work in this area that's specifically focused on urban energy systems modeling. So there's a lot of different bits in here, and because there's a lot of different bits, it's more or less an outline. And if there's any specific bits you're interested in, if there's quick questions, I'm happy to take them during the lecture. But if you want more detailed discussion, very happy to discuss after the lecture or in person anytime. Okay? All right, with that, let's get started. So as I mentioned already, the lecture today is basically about modeling urban energy systems. There's a lot of different bits of work that we're doing in Imperial College, both in the Center for Transport Studies and elsewhere, that hang on this general topic of modeling urban energy systems. And a good bit of that work centered around was partly kickstarted by, partly hung on a project that was called the Urban Energy Systems Project, which is basically what it means. And so the core of what I'm talking about in terms of developing a tool and what that tool can do, which I'll be talking about today, comes from that project, the Urban Energy Systems Project. Having said that, we successfully completed that project just early this year, and that doesn't mean the modeling work or the urban energy systems work is done. That's still going on, and there's a lot of development that's still underway. And the reason for that will become apparent as I go through the lecture, because it's quite an ambitious tool that we're developing. So there's lots of little bits and pieces that are constantly in development, and we want to do more with it. So this is the outline of my presentation today. I'll give you a bit of background and motivation, where we started from, a little bit about the UES Research Project, just so you know what the context was which brought all of our demand modeling work together. Then I'll briefly present the UES modeling tool, which is variously called SynCity or Urban. Why it has multiple names, I'll tell you later. And then I'll focus specifically on the disaggregate energy and resource demand models that are embedded within SynCity or Urban, whatever you want to call it. There are a number of different applications that SynCity can be put to. A few of these applications are in some of our papers. I'm just going to give you an overview of the kind of applications these can be put to. And also, my last slide, which is going to be about those applications, is also inviting people to join us and develop use cases that can demonstrate what something like SynCity can do. So we are actively looking for use cases, policy analyses, etc., that you want to test that a tool like ours might enable you to do. So we're very actively looking for those. So that's where I'll end the entire presentation, hopefully encouraging more collaborative interactions with all of you, or some of you. Okay, background. Some of this is, especially if you're here because you're interested in energy systems modeling, a lot of this is probably familiar to you. The statistics is now very wide public knowledge. Just over half the world's population lives in cities, and this is predicted to increase to over 62% or more. Some say 75, some say 80 by 2030 and thereafter. There's a spectacular growth in the developing world megacities, including Shanghai, Sao Paulo, and so on. And by 2020, it's expected, which is not very far away actually, it's expected that more than half of the mobile source greenhouse gas emissions could come from these megacities. So understanding and managing the energy use in such megacities that are developing with their old infrastructure in many cases is a key challenge. At the same time, different energy demand and supply vectors have evolved independently. Take a simple example of buildings and transport. Buildings and transport have for ages been modeled independently, have evolved independently, when in fact there's a very close connection between them, because people travel to get to building infrastructure where they then consume energy, and there's a strong connection between where they consume their energy and where they're traveling to. And so this current the current system works most of the time, but it's definitely suboptimal in its resource use. It's certainly unintegrated. If you think about several such examples of demand and supply vectors that could in fact be modeled together, but in fact have been considered entirely independently of each other, you realize that it's mostly unintegrated. It's certainly lacking in resilience, and this is not obviously a desirable arrangement for the future when there's a great need for efficiency and optimal resource use. So we need to be able to intelligently influence future energy and demand supply decisions, and in particular we want to enhance integration not just in planning these systems but also management and control of these systems. What I mean by that is not just being able to model these systems 50 years in advance or 60 years in advance, but also being able to predict and model these over a time frame of a day, over a few seconds, and so on, so you can have real-time management and control of these systems. So that was the objective originally of developing some kind of an integrated urban energy system modeling toolkit. In particular, we wanted models of urban energy systems that can serve as tools to understand and manage the demand for different resources in a city in an integrated manner, and moreover, to develop integrated models of urban systems that provide a more complete perspective, with the objective being an overall reduction in demand, and also to be able to analyze direct as well as indirect effects of policies. To take an example, if we excuse me, if we talk about this is not so much a policy as a technological, demographic, socioeconomic evolution. The fact that people undertake more teleactivities, for instance, telecommute and so on. There's been a lot of talk about how that might change resource and energy use profiles. What is not very clear is, if people work more at home, does that mean they're going to save energy overall because they're not driving to work? Or does it mean that they're now more inefficiently using energy in each of their individual apartments and so on? Now, you can hypothesize these kind of questions. You can even come up with common sense answers to them maybe, but there are no tools that can actually undertake some kind of an analysis of such a scenario, really. And that's what I really meant by both direct and indirect effects of demographic changes, scenarios, policies, and so on. And even wider. So that was just a very simple example to give you a hook. So that was what inspired, about 5 years ago, a little more than 5 years ago, the UES project, or the Urban Energy Systems Project at Imperial College. And it was a 5-year research program based entirely at Imperial College, funded by BP. And the aim of UES was to produce new models and methods to understand and optimize energy use in cities. In particular, the stated aim, quite ambitious aim, was to identify the benefits of a systematic and integrated approach to the design and operation of urban energy systems with a view to at least halving the energy intensity of cities. And that's quite an ambitious aim, which is partly why the project's done, but we're still working on it. Because we have tools, we've developed the tools and toolkits. So the initial bit, actually, we have up and running, and it's still developing. But in order to address the second half of this objective, we need to test a lot of scenarios. We need to put these tools to a lot of different users before we can come up with solutions to reduce energy intensity. Yep.
When you say energy intensity, that's energy use per unit service?
Yeah, exactly. Energy use per unit, whatever. It depends on what unit you're interested in. Right, so this project, as you can imagine, given that it has such an integrated framework, involves a lot of multidisciplinary collaboration within Imperial College. There are several research groups within our college working on this, including the Center for Transport Studies, Center for Process Systems Engineering, Electrical Engineering, Environmental Policy, and the Business School. So as you can imagine, just looking at this list, we have not just demand modeling components, which is what I'm going to primarily talk about, but we also have supply models, electricity network models, and water network models, and so on. Some of that is in the works, partly because of the difficulty in terms of getting real data. But yes, so it has all of the supply networks as well as the demand modeling components. So that was one of the advantages of having such a wide research group. The disadvantage really is that it's very difficult for each of the groups to understand the other. So we spent a good 1 year thereabouts just trying to understand what the other group was talking about. And although it took that amount of time, I can tell you that it was quite productive to spend that time exchanging ideas across different groups and exchanging language, jargon across groups, because I think it's this jargon to some extent that keeps all these disciplines separate from each other. And so I think the fact that we managed to overcome that, I wouldn't say we perfectly overcome it, but overcome it to the extent that we've built a tool that works in an integrated fashion, is one of the biggest achievements of the project as a whole. Incidentally, more about the project itself is available at this website. This website tells you mostly things about the project itself, whereas the modeling of urban energy systems at Imperial is a bit wider. There's lots of other bits of modeling work, both demand modeling as well electricity modeling and so on, electric networks modeling and so on, which are not necessarily directly related to the project. And so you won't necessarily find those at the project website, but if you're interested in energy systems modeling in a particular context, what you can do is go here, find the appropriate person to talk to, and then you can get a lot more about what's happening in that space than what you find in this website itself. So, so the objective of UES, and by this I mean the very specific objectives, the things we wanted to develop, was to develop a toolkit for the integrated model of demand and modeling of demand and supply vectors. Specifically, we wanted to understand and manage the demand for resources, so not just energy, going beyond energy, resource demand generated by the population. We wanted to analyze the interactions between urban subsystems, including transport, electricity, heating, water, and land use. We wanted to enhance integration in planning, management, and control, which are, for some reason, typically handled somewhat separately. And we wanted to analyze a variety of different scenarios and policies, which is where we are right now. And we also wanted to develop a tool that would be applicable to different study areas with minimum customization, if so desired. So we wanted something that's translatable, transferable. So those were the objectives when we started off. And more specifically, so I'm basically personally responsible for the demand modeling component within SynCity, and in general, demand modeling in the area of modeling urban systems. So the specific components for the demand modeling component in SynCity, in the UES project, were to develop a bottom-up, activity-based model of energy consumption that can, on the one hand, accurately assess behavioral responses to energy-sensitive policies, such as time-of-day pricing and dynamic pricing. On the other hand, to help develop policies that can target lifestyle modifications, get people to make choices that are more energy optimal. In particular, if you want to develop policies that are targeted lifestyle modifications, you need to be able to understand lifestyle choices and motivations at the level of the individual. So on the one hand, we wanted to develop that model of energy consumption, but on the other hand, we also wanted to undertake a lot of little bits and pieces of analysis, research, that helps us understand how people make lifestyle choices and what motivates their, ultimately what drives their energy consumption behavior, including things like the indirect and direct effects of technology holdings, ICT use, mobile phones for instance, smartphones, the choice of energy. Green Deal is one of the things we're trying to examine right now, how people make the choices. Car ownership, all of these, the impacts of all of these energy consumption. So this is more exploratory, modeling behavior, and that's more developing a predictive toolkit, a demand modeling toolkit. And also, fundamentally, the demand modeling component needs to provide inputs for more accurate modeling of emissions and air quality. And why we stress this amongst the objectives is that if you want to model emissions and air quality at a very disaggregate level, and my experience in this actually comes more from the American system of air quality modeling than the UK, I'm afraid, so pardon me for that. But if you want to model at that level, you really need fairly disaggregate, when I say disaggregate, both temporally and spatially detailed travel patterns of individuals and vehicles, which is why I mentioned something called disaggregate soak times. I'm not sure if the same term is used here, but in the US, soak time is the amount of time a vehicle is left unused, which then affects how much it emits or pollutes when it started. And in order to get that kind of detail accurately, you need very disaggregate, minute by minute, second by second often, models of travel flows and travel demand in general. So effectively, the objective of the demand modeling component is to analyze behavior, develop predictive models that are based on these analyses, as well as develop them at a level that's very disaggregate spatially and temporally, as well as not just spatially and temporally, but at the level of an individual decision maker or an agent. Just a quick background. So that was those were the motivations and objectives of the UES project. Just a quick background in terms of what we found when we went looking for urban systems modeling research that's out there. There are a few threads of urban energy systems modeling research that we found. One was integrated models of urban infrastructure, which are often optimization-based resource management models. And they are essentially targeted at the design of optimal and reliable generation and supply networks. And as far as demand is concerned, they typically use exogenous hourly demand predictions based on aggregate accounting, often rule-based methods, sometimes observed aggregate demands rather than behavioral. So in that sense, they're not necessarily responsive to the kind of policies that can affect behavior. What they do instead is construct scenarios of what they think, how they think these profiles might change under different policies. So in that sense, the scenarios are driven more by what the analyst thinks behavior will change, like, as opposed to fundamentally trying to get at that behavior change. Just a few examples of the papers we found there. Another thread of research focuses on extended land use transport models. And what these are basically they cover one or more aspects of modeling land use, mobile energy, that's transport energy, emissions, sustainability indicators. They cover one or more of these. And a few of them focus on ecological processes. Stationary sources of energy consumption, in particular buildings, are much less common. Having said that, there's a couple of examples that do take into account building energy consumption. Firms in general are only included for relocation choice, as opposed in the sense of trying to model where firms locate themselves under different transport system conditions, for instance. So these extended land use transport models do address some of the issues we're interested in, but in general they don't have a supply component. They do get at some of the demand modeling aspects we're interested in, but don't focus on the supply component that's entirely exogenous. Another thread of research that we found was on something called urban dynamics models, which focus mostly on non-transport urban systems, which is water, wastes, building heating, ecological systems, and so on. They mostly use methods of ecological and environmental simulation. For instance, there was a paper by Robinson, Campbell, and Geiser who assess energy, water, and waste consumption at a building or small neighborhood level. There's another paper that assesses the interactions of heat demand, locally available heat sources, such as lakes or incinerators. These are much more focused on ecological systems modeling, basically. There are very few studies that, those are the three broad threads, there are very few studies that actually integrated both supply and demand vectors. There was one that we found, amongst a few others, which was by Danielle et al., which integrates all urban subsystems, as the authors claim, natural, financial, human, and man-made subsystems. However, their approach is mostly top-down and aggregate analysis, which is designed for specific scenarios. So if you wanted to address a different scenario, you would have to basically tweak the models again, and it would again be top-down as opposed to bottom-up behavioral. The focus was not so much in behavior, but in taking into account all these different subsystems within an urban area. For the most part, they do not examine, well, they certainly do not examine both the demand and supply vectors with the same rigor. So this was just a cross-section of some of the papers we found, research that we found out there in modeling urban energy systems. If you're really interested in digging into what's out there in the literature, there's a, if I may say it myself, there's a really comprehensive literature review paper that we recently published with the objective of trying to really dig up what is out there, because modeling urban energy systems is a relatively newly developed field, and so there isn't a one-stop shop to find out what everyone else has done out there. And our objective here was really to try and pull those together. Some of the papers we found, in fact, weren't necessarily referred to as urban energy systems models, but they clearly were within the category that we're interested in. So we've tried to be quite comprehensive and not just sticking to something that's titled urban energy systems models. So if you are interested in digging into what's out there, definitely recommend that's a good place to start. Well, so that was the research. Having sort of identified the gaps out there, we set out to define a framework for what we wanted to develop. Effectively, we wanted an integrated modeling approach, as I mentioned over and over again. What do I really mean when I say integrated? We want the land use and agents. So in other words, where are the homes, where are the schools, where are the businesses, where are the retail centers, and so on, and how do people move within these? What activities do they undertake, when, where, how do they get there? So the land use and agent activities jointly generating demand. So this is bottom-up generation of demand, and the demand is for transport, as in other words travel, but it's also for energy indirectly and other resources. So that together generates a resource flow. I use the term resource because it covers all kinds of resources, including transport energy, heating, lighting, and so on. And then finally, there's the service networks that provide for this resource flow, that cater to this resource flow. And those are the supply network models. So effectively, we have four subsystems. I'll skip the first one for just a second and I'll come back to it. We have the agent-based microsimulation model of urban activities, or the AMUA, which is the subsystem that simulates the agent activities within the urban land use framework, or urban land use construct. Then we have the resource technology network model, which models the resource flows. And finally, the service networks design model, which attempts to design a network to meet the resource demands. Okay? The layout model is something we put in there with the objective of designing an optimal land use layout. Now you might say, if we had an optimal land use layout for London, could we really implement it? No, I don't think that's going to be that easy. One of the objectives of the layout model was that this entire modeling system could actually be used to develop greenfields or brownfield cities just as much as it can be used to analyze existing cities. And so the layout model attempts to, using purely optimization methods, attempts to define a city layout that can produce optimal resource consumption. Having said that, we acknowledge that you can start with an optimum as much as you like, but you're not going to stay there. The city is going to evolve. People are going to behave in different ways. Unless you force them to do certain things, which you can't really do, they're going to evolve. And so you start with a layout model, but then you let the AMUA model system tell you how people will behave within that layout configuration, and then derive what the resource demands or consumption looks like, and so on. So by introducing that layout model system, on the one hand, we develop a tool that can be used to design greenfields and brownfields, but we also develop a tool that helps us figure out if such designs are in fact optimal. And on the other hand, if you want to analyze a city like London, an existing city like London, then you don't use the layout model at all. This is a very modular system, so you don't have to use any of these specific subsystems, submodels. So you don't use the layout model at all. You use the existing land use layout for London as an input into the model system. And the reason we call it a city type down here was because we started with this grandiose objective of allowing this entire model system to be run on any city, basically. So we wanted to develop a generic model and be able to classify cities into certain city types, so that the model could then run differently depending on the city type. And that city type could itself be a combination of things like the presence of water, rivers, so actual physical aspects in the urban area. It could also be financial aspects of the city. What is the key industry that runs the city? Lots of different things. That was where we started. And I say that's where we started because we're still trying to figure that one out. That hasn't been very easy, to be honest. We've developed a model that works. We're able to implement it for London. We're able to implement it for a few other cities, and also for a few eco-cities in the UK at the point when they were pretty big. But in terms of making it truly generic, we're still trying to iron out quite a few issues with it. So that was the idea of the city type. So overall, this is the integrated modeling approach that we wanted to develop. Yep.
I see some of these arrows going both ways. Does it mean that you iterate between the
yes.
ones in terms of prices?
Yes. So the iteration is partly what allows for it to be integrated, because otherwise it's going to be simply providing inputs from one to the other, which is a very loose integration. The objective is for it to be truly integrated, and that's why you have arrows in both directions. Having said that, some of these arrows are currently working, some of them are still in the works. Any other questions? So that's the framework of what we're trying to develop. What do we want to be able to model in the city? How the space is organized, such as the built environment and its functions, the activity locations, the transport system, how agents use the space given the organization of space, how resource demands vary over space and time, which is fundamentally what we want to be able to answer. But also, what is the best resource interconversion technology and flow networks? I'm not an expert in that, but some of the other parts of the entire model system helps you answer those questions. What is the best engineering service network, and so on. So those are the kind of questions we started off with. So in particular, the layout model, given a city grid, will basically plonk buildings and transport on that grid. if you don't use the layout model, you start with buildings and transport layout, urban layout as it is in the city. So in this example, I'm showing you everything as a sort of a perfect grid system, the zonal system, but doesn't have to be. This is just for illustration. So London, obviously, the zones are not perfect grids. They're depending on if you're modeling. Typically, you can either model at the level of census wards, or in our case, we've mostly modeled at the level of the transport analysis zones, because that's the level at which we could get a lot of the data. But you could model at any zonal level, really. So you have the buildings and transport. Then the agent-based simulation level generates resource demands in that urban layout. And finally, the RTN model converts the resource demands into actual resource flow and conversion processes. So this is the flow. So this is actually up and running at this point. And the tool that does all of this is called SynCity. The first layout model, just to give you a brief insight into what kind of models, I keep saying model, and model means different things to different people, just to tell you what it means. The layout model in particular is a mixed integer linear programming model, so it's an optimization model. The objective is to minimize cost, energy, or carbon. It's implemented with a software called GAMS. Uses as inputs the spatial description, such as the size and location of the different zones, the type of buildings you have in there, high income, low income, the densities that you expect of the residential locations, of the residential areas, the available transport modes, aggregate activity demands in terms of how many trips are made of different work purposes, shopping purposes, and so on. So all of those go into the mixed integer linear programming model, come out, give you a location of building types and activities. So this tells you what is the ideal location for different building types. Gives you a transport network structure to connect these different building types and zones, and the indicative flows in these networks, which basically suggest optimum energy consumption. Therefore, the estimated costs, energy and carbon consumption. So that's the layout model. The agent-based microsimulation model for urban activities, which is my baby basically, is consists of the first component, which initializes the city. So you're not assuming that it's going to be a greenfield city, so you don't necessarily start with an optimal layout, though you could. But if you work with an existing city, you initialize the city, provide exogenous factors including land cover, land use, infrastructure, and a synthetic population. So we actually have loosely coupled with the AMUA module, we have a synthetic population generation module. What the synthetic population generation module does is it generates a population which is for all purposes identical to the existing population, for analytical purposes identical to the existing population. In other words, it has the same distributions of a variety of different socio-demographic factors, locational factors, etc., as the current population does. So in that sense, you don't work with the existing population because you can't for privacy reasons, but you work with a population that is constructed to be similar to the existing population. So that synthetic population generation module feeds in some of the exogenous inputs that go into the first step. Then we have the heart of the model system. And this, for those of you who are familiar with activity-based travel demand models, this draws from that. This draws from the methods that are used in activity-based travel demand models. So a lot of travel demand modeling, the state of the practice, I won't say a lot of it, the state of the art, not even the state of the practice, the state of the art in travel demand modeling runs on methods such as these. So I actually developed one of these model systems for travel demand modeling in Dallas when I was in Texas. So this draws on some of the learnings that I had there, and it's obviously translatable to this scenario because just like travel is an indirect demand or derived demand, a lot of resource demand is also an indirect or derived demand. People consume energy because they're doing something else in a certain space, for instance. So that was sort of the motivation for where this came from. So the core are two sets of models. There's the medium-term models, which model built environment and land use processes, such as where do real estate agents develop, where do people relocate to, Do they choose to buy a car, depending on how expensive it is to buy a car, how the transport system develops and so on. So all of the medium-term models go in there. Then you have the short-term or the daily models, which basically tell you what are the activity and travel patterns for the synthetic population. And this is where it differs from the activity-based travel demand models, which are primarily focused on what are the travel patterns. Here we're interested in what are people doing even while they're in home. Are they watching a film on their home theater system, which means they're not going to go into a theater, an actual cinema theater. What are they doing? Are they shopping online? So they're not going to go to the shop, but instead go somewhere else. So we want to be able to model not just where people are traveling to, but what they're doing, or at least what the synthetic population is doing. Yeah?
I was wondering how you handle different types of time. Would you give it a chance of the daily model, offer you a chance for seasonal demand, and annual chunks for GDP growth?
Yeah, so the more macroeconomic factors are modeled on a more time series annual basis. Things like the medium-term models, such as the decision to own a car, to buy another car, or the decision to relocate the household, or to relocate a firm, etc., are modeled on a, if I remember right, 2 to 5 year basis. About 2 years in some cases. You can figure out what frequency you want to model those at. Things like actual travel patterns are technically modeled. You could actually get this information on a second by second basis, but that would produce a lot of data. So usually for reasons of data storage capacity constraints, we tend to model them at about 5 to 10 minute time frame. Any other questions? Okay, so I'll show you another flow chart with the details of what goes into these in a bit. But effectively, that's what the short-term daily models do. And then we have an urban goods and services model system, which unfortunately is the least developed of the lot. It's there for a very good reason, because all these people who are undertaking activities are also consuming other goods and services. When they're shopping online, they're consuming retail products, goods. And that drives the urban freight, basically. Your deliveries, the plumber coming to fix your pipes, all of that's driven by the fact that people consume goods and services. And the fact that we know what activities and travel patterns they're involved in gives us the ability to model their consumption of goods and services, and therefore the supply chain activities that are required to meet that consumption. So that was the very good, very valid reason why we put this model in there, but we've had a lot of difficulty trying to get that model as realistic as, or as disaggregate as we'd like it to be, primarily because of data. So we can, at the moment, illustrate the use of this model using synthesized data that looks like the real data, but it's not quite the real data. But we're hoping to improve that further if we can get our hands, the more we can get our hands on some of the real-time data streams. There's some work in this area that's trying to use passively collected data sources to try and improve our ability to model these urban goods and services flows. Well, anyway, so those are the different model systems in there, and these model systems then feed into a set of energy consumption models that literally convert activities, transport flows, etc., into energy consumption vectors. Then finally, there is the RTN model, which is the Resource Technology Network model, which is also an optimization model effectively. It's also a mixed integer linear programming model. The objective is to minimize cost. It's implemented also in GAMS. It takes in as inputs the spatially and temporally resolved pattern of resource demands, which is exactly what comes to it from the AMUA model. So it's an output from the AMUA model that comes in here. It takes the available energy resources, available conversion and transportation technologies, and produces as output the resource distribution networks. such as, for instance, the number and position of conversion technologies, operating rates, and so on. Also tells you what the total system cost would be for that configuration. I think I might have missed the fact that we used the layout model for an ecocity case study, which was on that slide, but I won't go back now. You can go ahead and take a look at it. We applied the layout model to an ecocity case study, basically, to come up with different layouts of minimum energy and carbon and so on. This resource technology network model was applied specifically to a case study where we had a series of grid-like cities from about 10,000 to 200,000 population, and we tested a range of technologies available to meet heat demand, tested for the impact of planning restrictions on combined heating and power and so on. The AMUA model, we've been trying to, as I said, we're still in the process of a number of use cases. The first use case we looked at was different city configurations, land use configurations. We took London, Tokyo, New York, I think, if I'm right. So different kind of city layouts, trying to describe what those city layouts are, and then what are the implications of the city layouts on energy consumption, as AMUA predicts. And how, if we could change some of these urban layouts, what would be the implications on energy consumption. So there was a piece of work we did on that, and there's a paper that's currently in review with that case study, basically. But that's one of the few case studies that we're putting AMUA to right now. And I'll do my pitch again in the end. The service network design model, which you've not seen much of so far, is basically converts the macro scale network designs which the RTN model produces into more detailed engineering specifications. So this is actually network design for the supply networks. And it's concerned particularly with the design of robust urban power networks. And this one's currently under development. So SynCity, what you've been hearing so far is what SynCity is. It's the tool that embeds all these models that I've been talking about, the optimization models, the agent-based microsimulation model, all that's embedded in this thing called SynCity. It's an integrated modeling platform in Java, and it links the 4 submodels that I've just been talking about. There are 3 components in SynCity. There are a series of demand and supply models, which is the submodels I was talking about a minute ago. There's a unifying, so this is the engine. This is what does all the behavioral stuff. Then there's a unifying ontology and database to describe and store the core data objects. And then finally, there's an executive that assembles and coordinates the running of modeling scenarios, drawing from the demand and supply models, interacting between these. Okay? So that's effectively SynCity. The reason I said SynCity/urban is because most of the papers we've written on this refer to it as SynCity. So from a research academic perspective, it's known as SynCity. So if you search for SynCity, that's where you'll find the papers. But it's very recently been put through a commercialization process, and the first thing they came up with is you can't call it SynCity. And so it's being renamed to UrbN, which personally I don't like much because it sounds like urban, and that could be very confusing. But we'll see what it gets finally named. I prefer calling it SynCity because that's what we've been working on for about 5 years, so that's what it will be as far as the research team is concerned. So that's just the software architecture flowchart, basically. There's the executive in Java, there's a UES ontology, there's the database, SQL database, the submodels that I talked about, which is RTN, AMUA, the layout model, and so on. And you develop applications that draw on the bulk of that. The urban ontology. Now, what is an urban ontology? It's basically a common data model that represents the different urban concepts that we want to model. Space, agent, resources, process, technology, just to give you an example. And the reason we need ontologies, the reason we need these definitions is because we're trying to integrate across systems. And when you integrate across systems, you need common objects, basically, to integrate them. And these are the common objects that we use. So space is a physical space of the city as well as the hinterlands. Agents are the occupants of the city, including the households, firms, the government, for instance. Resources are the materials that are consumed, produced, or interconverted. These includes electricity, water, wastes, petrol, money, and so on. Processes converts one set of resources into another, for instance, an electrical generator. Travel also is a process in that sense. A storage process. So as you can see, it's these common terms, these common concepts that link the different systems that we're trying to model in an integrated fashion. Technology is physical objects that are required for the processes and agents to function. So that includes the transport network, roads, public transport networks and so on, buildings, the urban infrastructure, so all that falls under the broad category of technology. Right, so there should have been a slide in between this, sort of jumps into conceptual framework. What this is, this and the following slides are really what underlies the disaggregate demand modeling component in AMUA, in the agent-based microsimulation model for urban activities, okay? The conceptual idea for AMUA was that cities use energy as a result of human activity, economic, social, recreational, and so on. And so to understand and model energy in cities, you have to model this human activity. And the human activity itself is spatially and temporally distributed. Transport facilitates, constrains, and modulates all of these activities. So these are the idea that I mentioned a few slides ago, the idea that resource consumption, energy consumption is a derived demand, that it's these activities that are temporally and spatially distributed that drive resource consumption. That's just a schematic to give you an idea of what we're talking about, what drives AMUA basically. The fact that people undertake, individuals, households, etc., undertake a lot of activities both in-home and out-of-home, work, eat, shop, social activities, leisure activities, and so on. And they consume energy both in-home as well as in the buildings they are and out of home, as well as when they're traveling. So there's energy consumption in travel as well. And there are lots of trade-off substitutions between all of these activities that are driven to some extent by demographics, by transport policy, land use and accessibility, economic activities, by the fact that people are intrinsically heterogeneous, their use of technology, and so on. And these activities, the land use, accessibility, economic activities, and the individual household activities as well, are correlated or generate firm activities which supply the goods and services that people consume basically. You have both business to consumer activities as well as business to business activities. That itself consumes energy, as well as the demand, travel demand generated by these activities also consume energy. So that's sort of the comprehensive picture of demand that we're really trying to capture. And the specific elements of this framework is that it's disaggregate, spatially and temporally. I mentioned this a few times. The demand is at the level of the individual. I should say agent really, because it could be an individual, it could be a household, it could be a firm. There's an integrated treatment of the production as well as the consumption activities of these agents. We attempt to model at least not just passenger travel and passenger activities, individual household activities, but also urban goods and service flows and firm activities. Overall, plan to use a microsimulation approach with a random utility maximization based agent behavior models. For those of you familiar with discrete choice models, these are primarily discrete choice models, though not all discrete choice models. Some of them are also continuous models, such as hazard duration models and so on, in particular for time. And so it doesn't use just a cost minimizing technology choice, but a descriptive agent behavior model. Okay? And finally, we want a systems level integrated supply network that integrates with this demand model. So those are the elements of the demand modeling framework we developed. I'm running a bit out of time, so I'm going to go through. I actually described all of this in detail earlier. So AMUA is the agent-based microsimulation model of urban activities. It has a lot of sub-models within it. And the next, basically, 3 slides present these sub-models. So to begin with, we have exogenous factors, such as weather, land cover, governance, structure, pricing index, economics, and so on. Then we have a few indices that we develop. And we come back to these indices when we have modeled the city as well. Then we have the synthetic population. This schematic shows the synthetic population is a part of AMUA, but at the moment it's manually linked. So we do the synthetic population generation and then plonk that into AMUA. Then we have the medium-term models, which includes residential and work choice models for the household agents, where they choose to locate themselves, where they choose to work, and so on. So these are decisions that they re-evaluate every few years and might change depending on how expensive things become. If traveling is expensive, if cost of land is expensive, buying property is expensive, accordingly drives where people locate themselves in the urban area. Their vehicle and technology holdings models. This is about their choice to own cars, but not just own cars, but also to own the latest technology, the smartphone, the home theater system, and so on. Then there's the land use models. These are the other agents, the real estates, businesses, policymakers, and so on, who drive what happens to the land use, where developments are made, where the transport system is developed, and so on. And then we have the short-term daily models, which generate the activities that the individuals and households perform. And as I mentioned earlier, this is both the in-home activities as well as the out-of-home activities. Then there's the activity scheduling models, when they perform these, where they perform these, what mode they use to get to these models, and what routes they choose to get to these models. So these are classically activity-based travel demand modeling. This is a classical activity-based travel demand model system, basically. The one component over here that's not typical in most travel demand model systems is the fact that we do a fairly detailed generation and scheduling of in-home activities, which are not a part of travel demand model systems, because we're interested in what people do in-home and how it affects what they do out of home and so on, and how it affects energy consumption as well. So the outputs over here are a string of activities by location, time of day, use of technology, which then feeds into a set of almost conversion factors at this point, telling you how much energy is consumed, what the energy demand is. And then we have the supply chain models. I've sort of put it in here at the end because this is the least developed of the lot. But this effectively tells you how the firms behave and how they supply the goods and services that people consume. And there's another paper which was presented, which has recently been published in the Journal of Industrial Ecology, which presents this activity-based approach to modeling energy and resource demands. So the bottom-up means of modeling energy and resource demands. So it presents this framework effectively. There's a couple of schematics here which are just to give you a sense of the kind of detail that goes into modeling activity patterns. So this, for example, is a typical worker's day pattern, a daily pattern. So the day starts at 3 a.m. on day D, ends at 3 a.m. on day D plus 1. And over those 24 hours, the person stays at home initially, leaves home for some non-work activities, maybe to drop off the children, maybe to pick up the milk in the morning because they don't have any or something. So there's a few activities before going to work, comes back home, and then leaves for work. So there's the commute, has to get to work at a certain time, stays at work, while at work maybe goes somewhere else, maybe to have lunch or maybe for a quick shopping trip, stays at work some more, leaves work at a certain point, travels on the way back home, does something, no idea what, stays at home, and then there's an after work tour, maybe goes out to meet friends and so on, stays at home. So in the most complex scenario, a person could be doing all of these. Though in reality, you don't have all of these happening. You have some subset of this happening. But this pattern, this chain of activities, is just to show you that we're basically trying to model at that level of detail. So that we can say, if this person, while at home here, does his shopping, then it's quite likely that none of those trips were really shopping trips. There was something else. Okay, so these models feed into each other to allow trade-offs between the different activities that the person or the household, in fact, undertakes. And there's a similar schematic for a non-worker. It's simpler for a non-worker because you have a number of home stay durations interspersed with tours, and the tours themselves could have any number of stops on them. And that's just an example. So the thing with such a model is, this is a transport policy example. The thing with such a model is if you have something like an early release from work policy, about 10, 20 years ago, 15 years ago maybe, there was a big move towards having work leaving time, what's the word for it? Staggered work leaving hours. And the idea was that if you got some people to leave at 4 o'clock, some people leave at 5 o'clock and so on, there'd be less congestion out there. But the fact is, if you start modeling the activities that a person performs, but more importantly, if you account for the fact that people are very heterogeneous, what drives their desire to travel, to go somewhere, then you have patterns such as these. So for instance, there's this person who normally leaves work at 5 o'clock, 5:15 gets to a shop, does shopping for about 25 minutes, and gets home at 6 o'clock. Now you let the person go at 4 o'clock, and the person actually prefers going to a shopping location that's further away, but didn't used to go there because he didn't have much time before he had to get home. And so now he drives much further, drives about 30 minutes to get to this different shopping location, spends longer shopping there because it's a shop that he likes, so enjoys shopping in, and in the process ends up leaving the car sitting around long enough that it's the cold start when he leaves the shopping location, and then gets home at 6 o'clock anyway, so he's still on the transport network. Right? So these heterogeneities, individual behavioral aspects, are best captured if you can model that person's pattern, for instance, and preferences and behavioral tics, if you will. And so that was this was actually one of the case studies that we applied to an activity-based travel demand model system in Dallas and demonstrated the impacts of taking some of these into account on the policy itself. So we'd like to look at similar policies, similar examples of energy and resource use policies to see how the models can actually show these indirect, unexpected, if you will, impacts. The important thing about any policy analysis is not just to be able to predict what you know will happen, but to be able to predict what you don't really expect will happen. And for that, you need to be able to capture or have an inkling of what other kinds of behaviors people might exhibit, what heterogeneity there might be in what people do. And so in our own way, that's what we're trying to do. It's not easy, but I don't want you to go away thinking this is as easy as just doing that, but we're trying to get there. And the models that we've been developing do it to some extent, with tics, with bugs and so on, but that's what we're working to fix. So finally, some of the policy scenarios, use cases that we hope to be able to test over the next year or so with SynCity are infrastructure-oriented policies where we can do more detailed cost-benefit analysis and impact assessment for investment. And I don't mean just transport infrastructure, I also mean energy infrastructure, water, wastes, and so on. Demand management policies, looking at direct and indirect effects of mobility taxes, smart metering, the combined effects of time of day, road and electricity pricing, for instance. People keep talking about electricity pricing, we keep talking about road pricing, but never think about what will happen if they both acted together on people, basically. What would they behave? Especially if you had more electric vehicles in the system. So this is something that we've already started looking at. There's a case study we're working on to see what the impacts of electric vehicles would be on, now that we have a model that can, in an integrated fashion, model both electricity and transport. The obvious example to start with for us was electric vehicles. What will happen to the system if you had electric vehicles? So that's one of the case studies we're looking at. We want to be able to model lifestyle and behavioral changes, how, when, why people make smart choices or don't make smart choices, and to be able to look at how those then produce some of these indirect effects that I'm talking about. Looking at demographic trends, what are the impacts of things like aging populations, global mobility, the fragmentation of families, the impacts of new developments such as digital mobile services, low energy vehicles, and so on. Some of these cut across, actually. Some of these scenarios cut across. They're not all independent. So these are the kind of scenarios we like to do. We like to be able to develop solutions of different kinds, engineering solutions, technological solutions, as well as policy, baskets of policies that will work towards specific objectives. So this is the reason that we started developing SynCity. We're still developing it, and goes beyond the Urban Energy Systems Modeling project, and we continue to look at disaggregate models of demand and behavior, basically. There have been a lot of challenges, certainly. All of these subsystems are developed in different platforms. They speak different languages. They have different geographical resolutions, temporal resolutions. I won't go into all of that in detail. One of the key challenges for us at the moment, the most important one in fact, is validation. We have validated bits and pieces, so we validated specific subsystems, but validation of the whole thing is an entirely different matter altogether. In particular, when you're validating the whole thing, you have to account for the fact that errors can propagate through the system. And in order to be able to take that into account, we need more robust validation, really. So that's one of the things we're very high priority working on, basically. That's pretty much it. That just summarizes what I've been saying, so I won't repeat that. Since I didn't have too many questions while I was talking, I'm hoping they'll come now.
I'm sure they will. Thank you very much for a fascinating talk.
Thank you.
Any questions?
Yes.
You say very complex. You must very simplistic type of model, and you're saying is going to provide outcomes which are going to be useful. And I wonder whether in fact it's only useful for a brand new city of the type that you described yourself, which you're trying to get some feel for. I suspect that an urban planner who has some innate knowledge of how cities work might actually come to conclusions which are more useful rather than using models like this, which are essentially of themselves.
Well, I'll come at this question backward. To begin with, we've actually used this model system for policy scenarios for a city like London. So we're not talking about greenfields, new cities, but an existing city with all its complexity. And we get results that are what you would expect. So what if you as a planner had an intuition of how the results should be, the results are fairly intuitive, except they give you more quantitative results, which you can actually then use to drive, for instance, things like cost-benefit analysis, appraisal, and so on. So I think I'm fairly confident that the models do deal well with real cities based on actual empirical examples. But coming back to the first part of your question, I do agree there are simplifications. There are more simplifications in some parts than there are in other parts, and that's something that will constantly keep evolving. And accordingly, there might be some policy scenarios that it might be less, in its current form, less equipped to deal with than others. I'm trying to think of anything particular here. For instance, I've been talking about things like e-shopping. E-shopping being something we want to be able to analyze the impacts of on the urban system. Now, we'd like the model to be able to do that, but in its current form, it's going to be a bit poor in that bit, in modeling the impact of e-shopping, simply because the urban goods and services model that I mentioned is amongst the simplest components of the entire thing. It's amongst the most toyish component of the lot, just because we didn't manage to get the data for it. And since the impacts of e-shopping depend heavily on what will happen to the urban goods flows, that bit won't be modeled very well. So yes, at the moment it won't. We hope it will eventually, but at the moment it won't. So there are examples of some policies where you're right. It would be simplistic. But that doesn't make it useless for all policies. I mean, that's not really a question, I guess that was a comment, but that was my response to it, so yes.
How do you deal with consent issue?
The what issue, I'm sorry?
Consent with your data gathering. Presumably you're gathering from supermarkets, utilities.
Yes. That's the hardest part of what we're doing, actually. Some of the data is gathered because we have relationships with certain retailers for specific projects. So one of the projects that Andreas mentioned in the introduction to me, I guess, was the Digital City Exchange project. And as a part of that project, for instance, we have relations with retailers such as Sainsbury's. And so we get data for which will hopefully help them eventually in modeling how they best use their energy, but then that also contributes to what we're doing. We don't actually end up using the data as is. We use the data to build models, which are then used in our model systems. So the models, these models are really econometric statistical models that are built on data. So they extract behavioral patterns. They extract relationships from the data, and then those go into SynCity. So we're trying to overcome it through these relationships, but that is the hardest part of what we're trying to do. The easier data to get obviously is the bit that's accessible through things like the ONS, more widely available data.
So you have a data set, and then you model and get a behavior pattern. And then how do you extrapolate any change?
It really depends on the kind of behavior you capture in your model. So if you take, I'm going to reduce this to a simple model. In reality, it's not just one model, it's a whole series of models. But if you had a model that, let's say, is a regression type or a discrete choice type of model, which is modeling the, let's say, the type of energy that a person wants to purchase or invest in. And you could have a lot of explanatory factors there. If the only explanatory factors in there are things like household size and household location and so on, that would be purely descriptive. If on the other hand you had variables in there that captures the household's elasticity to prices, for example, because elasticity is the most commonly used aspect in policy making, then that model becomes slightly more behavioral than it would be if it had only descriptive variables in there. And so we try to get in as many of those as we can, given the data, obviously. Limitations might arise from what the data actually contains, but we try to get as close to elasticity and behavioral aspects as opposed to purely descriptive models. Yeah.
My sister thinks London stretches all the way to Cambridge, but I think it stops at Zone 2. So how do you define a city? How do you deal with the inevitable system boundaries?
Yeah, no, that's a very good question, because we spent a long time in the beginning of the project trying to figure out where to draw the boundaries for a city. And eventually we figured you just have to be practical and draw them where you can get data best. In other words, if you can get data for the Greater London area from the Greater London Authority, that's a convenient boundary to draw. So that's sort of where we ended up with for the models. For London, that is actually the boundary we have drawn. It's the Greater London Authority area, which is just slightly beyond the M25 in bits and pieces, basically. For the most part, I think we will be driven, for other cities, we will be driven more by what their planning authorities use, their metropolitan planning authorities use as the city boundary, and treat the rest of it as not necessarily exogenous, but external zones which generate travel, but we won't go into the details of what those people are doing. So we won't model them in the same detail as we do our synthetic population in the study area, but they do contribute to travel on the network. So that definition then gets a bit blurred when you talk about energy production and so on, for which we want to have a slightly wider boundary. And in this instance, I think we have a South-East England concept for energy production as a whole. I wouldn't want to say more than that at this point. I'd have to find out exactly what the boundaries are for those models. But yes, that's a very good question. You could choose different boundaries and so on. We chose to go with practicality more than anything else.
It's about sensitivity. And how much do you have to change the inputs before you notice a difference in the outputs? And kind of related to that, if you were to use it to predict the layout of a new city, if you built the city very slightly differently, how much would that take away this optimal energy use that you've been predicting for it?
The first question is actually a little too general for me to answer, because in terms of how much changes in the inputs changes the outputs, depends a lot on what inputs you're changing and what outputs you're talking about. And there's way too many inputs and outputs in that image over there. So it's hard for me to say exactly what that is. There are some variables which are more sensitive and some less so. It entirely depends on the context. So if you had a very specific idea in mind, maybe I could answer to that.
Not so much, I was just kind of interested in how much you know the sensitivities and which variables are most sensitive, and whether you can really imagine that, or whether the whole system gets so complicated that you can't actually know the effect of changing the the inputs?
No, you do see the effects of change inputs. To take an example, one of the many models in the AMOA framework that I showed you, the flowchart that I showed you, was a short-term model which tells you what mode choices. I'm zoning into that because the mode choice model is sort of very easy to talk about more than anything else. And that mode choice model would be very sensitive to travel times and costs. So if you changed travel times by a particular mode significantly, you would see a significant change in the kind of modes these people use, which would then impact how much time they're spending in the network, what energy that mode consumes, and so on. So how much of an impact does that have on in-home energy consumption? Probably not much, because we're assuming they're traveling in the same times, just by a different mode, etc. So again, if you want to know how much of an impact it has on outputs, it depends on what outputs you're looking at. It will have an impact on transport energy consumption, not so much in building energy consumption. So we did a couple of, my memory is failing me at the moment. We did a couple of case studies where we tried to look at the relative changes in total energy consumption of building infrastructure, transport infrastructure, and the city as a whole, which is basically the sum of those, for a few scenarios. And the scenarios we looked at least produced significant differences in these energy consumption vectors. Now I can't quite remember what we put into that scenarios, I'm afraid, so I'll have to go back and look into it now and see. Your second question was?
Kind of related. If you say predict the layout of a city and it gets, hypothetically, it gets built slightly differently, to what extent have you, do you take away from this optimum energy use you're trying to achieve? How much does energy use go back up again?
That we've actually tested. We tested that, I think, for Marstonvale. And the model as it is, at least, definitely shows how much there is a difference in that minimum energy scenario that we originally designed it for. And it also tells you where spatially that is affected the most and so on. Again, I can't remember exact numbers or percentages. I'd have to go back and look at the results to tell you, but I'm happy to share the Marstonville case study with you if that helps.
Now I heard the bell clock reminding us that we are already all over time, but there's one last question, if there's a quick one.
Yep.
You mentioned commercialization. Just wondering, what type of organisations did you intend to sell or license the tool to?
It's still very early, so I'm not sure where this is going to go. But we hope to be able to apply these tools for policy, so planning agencies, for example, consultancies. So BP is actually, well, not a consultancy, but an industry. BP is actually interested in using something like this to look into future scenarios, where to position themselves and so on. So at the moment, we're looking primarily at businesses and planning agencies. Have to think further about that.
I'm sure there are many more questions, and Aruna, I hope, will be available for some time upstairs in the first floor, and you're all invited to join us. But before we do, let's give her another round of applause and hope that she will come again and show us results about New York, Tokyo, and London, right?
Yes,
So,
yes.
Thank you very much.
Thank you.
It's so great, I would have never realized it. Out of breath, I can't imagine how you